Hello everyone, welcome to Feature Engineering series in Python tutorial number 4. In previous videos, I have already covered how to handle rare labels, how to improve the accuracy by handling the cardinality, and what are the missing values, whether these values are missing randomly or not. So these analysis in last 3 tutorial I have already done. This is the 4th tutorial in this series, and in this lesson I'm going to discuss about what is the linear model assumptions in advanced linear regression. Whenever you apply linear regression, you make some assumptions in your data follows some kind of these assumptions. Alright, so while me discussing these things in detail, this is just introductory. Alright, so these things we'll be discussing throughout this video series. What are those assumptions? Thereafter, I'll be discussing these assumptions with the definition and how we make sure that we meet to these assumptions in our data set and how to check these assumptions. Alright, so to check the linear model assumptions, we have to analyze our data set. So I'll be creating here a reference data set, and then I'll be showing you with the various statistical analysis and various type of the matplotlib and the seaborn plot whether our data is following a linear model assumptions or not. If it is not following, then we have to do a log transformation so that it can follow a linear model assumptions. So we'll be doing it on the Boston dataset, and we'll be doing it mainly on the 3 column, but you can extend it to all other columns. Thereafter, we'll be also discussing about the co-linearity, and then I'll show you how you can check it. And then finally, I'll be showing you how you can check a normality of the data, which is, whether it is normally distributed or not, with the various methods. Thereafter, I'll be showing you the homogeneity, which is the homoscedasticity. Homoscedasticity of data shows that how homogeneously this data is distributed along with the input feature vectors. Alright, so I'll be showing you all those things. Thereafter, at the end of this lesson, I'll be showing you with the help of log transformation, how with the help of log transformation you can improve the accuracy of your machine learning model. But there are still some of these outliers which we will be discussing in the next lessons. And this is going to be a large video series on the feature engineering. So please do not forget to like this video and subscribe this channel so that whenever I publish new video, you should get a notification in your inbox directly. Alright, so without wasting time, let's go ahead and get started with this lesson. I'll be showing you a line by line code with the complete explanation. Alright, so without wasting time, let's go ahead and get started with feature engineering series in Python tutorial number 4. Previously, we have seen how we can handle rare labels, how we can handle random values, and how we can handle variable cardinality. Now in this feature engineering series, I'm gonna discuss what is linear model assumption in advanced linear regression. I mean to say that when we develop a linear regression model, a machine learning model, we do a lot of assumptions on our input data so that it can fit accurately on our regression line. So what are those assumptions which we make? In general, you may not know this, or you know this, you make few of these assumptions which is automatically made. When you are a beginner in a machine learning, so these assumptions you have already made. You may not know about this, but when you apply machine learning model, you assume that these conditions are satisfied in your input data. If machine learning model fails to satisfy any of these conditions, it may poorly overfit or underfit. So what are the examples of machine learning models which are linear? So these are a linear machine learning model like linear regression and logistic regression, linear discriminant analysis, and principal component regressor. So these are linear machine learning models. What are non-linear models? Deep learning models are a non-linear model because we have their activation function. So the activation function makes our input and output correlation like non-linear. All right. So in these linear machine learning models, we need to provide a linear data. All right. I mean a linear model where these conditions are satisfied. I mean on the data, these conditions are satisfied. So the first condition is there should be a linear relationship between x and y. There should not be any co-linearity between input feature space. That's mean on the variables of input variable x, and there should not be there should the input variable or input features, they should be normally distributed. A normal distribution, I'll explain that later. And the fourth point is homogeneity of variance. That's mean it is homoscedasticity. In homoscedasticity means that the errors are distributed along whole data and it is not concentrated at a particular point of the data where you are getting most of the error. Alright, so the error is concentrated, randomly distributed along the whole data points. And if you plot normal distribution of the error, then you should get the error the concentrated around the 0, and then there is the declining valley before and after the 0. Alright, so these things I'll explain later in the video series. So let's go ahead and first see what is the linear relationship. In a linear relationship, when the target variable, which we will be taking as the price of a house, because we are going to discuss here a Boston housing dataset, in that case the price of house is a target variable and the input feature space, those are independent variables and those are represented as a x vector and this is the y. So in the x vector, if there is a linear relationship between x and y, then the combination of with the combination of x vectors we can get accurately y. That's mean beta 0 plus beta 1 plus, into x1 plus beta 2 x2. So kind of these. So these are the linear combination of input feature space. Based on this we can get the output. That's mean that is a linear relationship. If linear relationship is not satisfied, in that case our model may not perform well. Alright, now let's go ahead and discuss about the second assumption, which is normality. A normality means that every variable x follows a Gaussian distribution. In a Gaussian distribution, it is concentrated around the 0, that's when there is a peak, and then it follows a normal distribution. So this one is the second condition for a linear model assumption, and thereafter we have a multi-collinearity. There should not be a multi-collinearity, that's when there should not be input variables correlated to each other. And if variables are correlated to each other, then they will overfit your machine learning model. And if we see closely our dataset, Boston housing dataset, we will find out that there a nearby distance and nitric acid concentration is correlated to each other. In that case, if we consider these two models together, then there is going to be overfitting in our model. So later I'll show you a complete analysis of a Boston housing dataset, but these are some introductory level of explanation. So let's make assumption that we have a Boston housing dataset. Alright, so we have to drop at least one column while considering our final machine learning model training. This is the third condition. There should not be a multi-collinearity. And in the fourth condition, we automatically assume that there should be a homoscedasticity. That means a homogeneity. A homogeneity means that the error, alright, which is also known as the residuals, it is distributed along the whole data set, and its distribution is somewhere around the 0. And if we see here a real data plot of residual, that's the residual means the error in the predicting actual target the house price with the input, that's the lower status population. So we see that they're kind of a normal, a homogeneity is there, but it's not the perfect homogeneity, but we can consider that at some level there is homogeneity in this data. That's mean the error is concentrated around this 0, and then it is also distributed around all the variables values. And although there are some outliers we can see, so in some other lesson we will also see that how we can handle the outliers. So these are the 4 examples which we make the assumptions while considering our linear machine learning model. Those 4 assumptions, once again I'm going to list those. Those are linear relationship, normality, multi-collinearity, and homogeneity. Alright, so these are the 4. Now the question comes, how can we evaluate if the assumptions are met by the variables? That's mean how we can do the evaluation whether our variables are following these assumptions in our linear machine learning model. So for that we have to do the analysis. The analysis which we are going to do in this lesson, like the linear regression. With the help of linear regression, we will try to establish that whether a particular the input variable is linearly related to the target output or not, and we will be also plotting there the scatter plot, and we will be also doing the residual plots. That's the error plot. For a normal distribution, we will be using here a QQ plot. The QQ plot is a scatter plot created by plotting 2 sets of quantiles against the one another. Alright, so don't worry, I'll show you these things in detail. And the third point, we can make sure that whether it is following or not, that's the multi-collinearity. And we can access the multi-collinearity by a correlation matrix. And there is a homoscedasticity. In homoscedasticity means the homogeneity. This can be assessed by the residual plot. That means the error plot. So I'll be showing you these things in detail. Thereafter, what we can do if these assumptions are not made, that's mean, let's say we had analyzed our data and we found out that there are some variables which do not satisfy these assumptions. Then what we can do to satisfy these assumptions? So to satisfy these assumptions, we can do either one of these 2 things: mathematical transformation of the variables and discretization. A discretization means we can discretize our input variables. We can group them to find to make sure that it is satisfying these conditions. Otherwise, if we can't do the grouping, we can do a mathematical transformation. So in this lesson, we will be focusing on a mathematical transformation. That's mean we can do some transformation like a log transformation or some other kind of the transformation to transform our data from one scale to another scale so that it can satisfy these assumptions. So overall in this video lesson, I'll be covering these 4 points. The first one, I'll be doing a scatter plot and residual plot to visualize a linear relationship between input feature space and the target variable. And then the second, I'll be doing here a QQ plot for a test of normality. Thereafter, in the third part, I'll be doing correlation matrices to determine the collinearity and the residual plots for homoscedasticity. That's mean for homogeneity. Alright, so without wasting time, let's go ahead and get started with this lesson. So I have imported only few columns here, just the first row here. In the first row, we have here a complete the libraries. Alright, so in this complete library, what we have here, we have a pandas imported as a PD, numpy as NP, and then we have a matplotlib.pyplot as a PLT, and the seaborn as SNS. Thereafter, we have here a QQ plot. The dataset for the demo, we have here sklearn for dataset import, load dataset. For a linear regression, we have imported linear regression, and for a split and standardization, we have imported here trend, test, split and standard scalar. And to evaluate the regression models, all those things, we have here a mean squared error. All right. So these things we have imported here. We will be utilizing all these Python packages throughout our video series. All right. So before we check a linear assumption, we need to load our Boston data set. So let's go ahead and load this Boston data set. So to load the Boston dataset, what we can do there, we can say here data is equal to load Boston. We have already imported this load Boston from scalar. So there we have our data. Now do you see this data is kind of the dictionary? It has many keys there. So the keys are like data, target, feature name, description and the file name. Alright, you can also see overall description. So like this one. If you print it, you will see there Boston house price dataset, and it has here a complete description. You can read it. Moreover, it has these columns as an input. This is the input feature space, and this median value of owner occupied home. This is a kind of home price which we need to predict. So this one will be a target variable. All right. Perfect. Now let's go ahead and save this whole data set in the form of pandas data frame. You can simply do it like pd dot data frame, and thereafter we have here a Boston data frame data dot data. So this one is data, and thereafter we have here the columns. In the columns we have here data dot features name. So these are the column, and if you run this you will get something like this. All right. So I'm going to simply store this in the Boston, a new data frame which is Boston. All right. Perfect. Now if you see this Boston, what do you get there? You get there a 13 column, and out of these 13 column we do not have a median value. All right, so which is a house price, and this median value is stored in the target key, I mean this one. All right, so we need to store that. We need to store that in the Boston. That's the median value is equal to data dot target is there. All right, so that's how we get this data dot target. Thereafter we once again see here our Boston data set. Now we do get there a 14 column, and the last column is median value of a house price. All right, so it is represented in thousands of the dollar. All right, perfect. And if you want to also know about these features, so these features are actually the data dot features name, which is this one, and we are gonna simply store these things so that we can use these features later on. All right, for the purpose of our analysis, data analysis. All right, perfect, superb. So we have got our data set. It is stored in the Boston, and thereafter we have our feature space input vectors. So we'll be doing our complete analysis on this part. All right, perfect. So for a complete analysis, we also need to get our perfect data, because for a comparison, we will be needing some data which can compare how actual distribution or actual assumptions are, and what type of the assumptions we consider from this housing data set. That means to say that we need some kind of reference to compare our assumption, and for that reference we are going to create here a reference. All right, so there I'm going to say that create a reference data set. So for creating a reference data set, we need to create a random data set. All right, for that one, we have np.random.seed, and inside that, I'm going to feed the 0 so that we can reproduce the same result every time. There n is equal to, do you see there, 506 rows. So I'm going to say simply there the Boston dot shape 0. All right. Thereafter, we have here x is equal to np dot random number distribution. All right. So this is going to create an n number of random distribution. And for y, I'm going to just get that y is equal to, that's actually y is equal to x multiplied by 10. That's mean I'm generating data which is linearly related with x. All right, 10 times of x. Thereafter, plus np dot random dot rand n number of times, and then multiplied by 2. So I'm just adding some noise. Moreover, I'm trying to generate a data set as an input x and the output y to compare this Boston housing data set. If you remember previously, I told you that we will be evaluating our input feature space with the target variables to understand the linearity, normality, multicollinearity, and homogeneity. So these things we need to do with some reference, and for that reference I'm gonna take it from our this demo data. So once we have our input x and the y, thereafter I'm saying here, there we have our demo data frame is equal to pd.data frame, and thereafter we have here our x and y dot t, that's the transformation. All right, thereafter we once again have a demo underscore df dot columns, and in this column I'm gonna set here our input x and the output target variable which is y. All right, let's go ahead and see our demo df with some head, that's mean first 5 rows. So there we have our, and this is going to be a reference data for our analysis of a Boston housing data set. All right, so what we are going to do here, the first we are going to do a linear assumption check. All right, so let's go ahead and check linear assumption. All right, for Boston data set. So in the linear assumption, we need to do a few things there. The first of all, we need to create here a reference so that we can compare our Boston housing data set. And for that reference, we are going to first plot this demo df. All right. And the linear assumption, we will be checking with the help of a scatter plot, and then we will be checking how the inputs are related with the target output. So we have here sns.lm plot. There we have x is equal to x and y is equal to y. And then there is data is equal to demo df. And the order of the fitting, I'm going to use here 1. Do remember, if you are new to Seaborn Python package and Python library, you can watch my Seaborn tutorial on YouTube. So there you will learn everything about data plot with the help of Seaborn. Thereafter we have a plt.y label, and in that I have here a target. Thereafter plt.x label, and in that I have here independent variable. All right, so that's the x input variable, and if you plot this, you will see something like this. And if you notice, this is highly linearly correlated to each other. And do remember, we are talking only about the input feature space and the target feature. All right, we are not talking about the only input features. So the input features and the target feature, the target variable should be correlated to each other, and that correlation should be a linear correlation for a linear machine learning models. All right, perfect. So this is check on our demo data set. Now let's go ahead and check it for our Boston housing data set. And in that, I'm going to use here LStat data. All right. So this LStat is this LStat means the percentage of lower status of a population, and the Y is median value of house prices, and in the data we have here a Boston data. All right, and in the target we have median value, and there of course we have here LStat. So it's like this. Thereafter you can do like the plt.show to remove this text data. Now what do you see there? You see there is a huge difference between the first plot on our demo data versus the plot on our Boston housing data set. So the moreover, if we see in the range of these data set, we can see this is a linearly correlated. This LStat is linearly correlated with the target output. But if you see at the start of this LStat, it's not linearly related. There is an offset. In that, what's the offset is there? If the population is really very low for low status people, that's mean if there is the area which is surrounded by people living with a high status, then of course the prices of house will be pretty much high. So at the start of this, it's obvious there, but thereafter it has started decreasing linearly. So we see there a linear relationship, but we don't see here any linear relationship. It means to say that if you apply your machine learning model blindly on this dataset, linear regression dataset, to calculate the final house price, then it's not gonna give you the best result, because your model is not linearly related with the input feature space. That means the target is not linearly related with the input features. So we need to do here some kind of the transformation, which we have already talked at the start of this video lesson. Now this is for the only this variable. Let's go ahead and check it for some other variable. The other variable I'm going to check here is let's go ahead and check it for something else. Okay, one more thing I should show you that we are using here only order 1, but if we increase this order 1 to 5, let's say, in that way you will get that it is now kind of properly fitting, and it's following this line. But do you see there it's order 5? That means this is not a linear relation. It is having a non-linear relation. There is a non-linear relation between the input feature and the target feature. So we need to also address this in our transformation. Alright, superb. Now let's go ahead and plot it for some other input variable. So I'm going to plot here with the RM. So RM is average number of rooms, and there is Y. Alright, there is everything is fine there. Sorry, that RM should be here. Now if we plot this, what do we see there? So at the center of our data set, there is a linear relation, but at the end of this room number, there is a high spike in the room, in the house price, and there are some other outliers are also there. So the moreover, once again, it proves that there is no direct linear correlation between these two variables. So that means to say, if you have been applying your linear regression model blindly on the input data to predict the target output, then you are doing it wrong. I mean, you did not do any of the input data analysis to understand that how it is working. So the moreover, you are doing it completely wrong, and in that way it might not produce you a best result. All right. So after some time, I'll be showing you what kind of the transformation you can follow so that it can follow a linear trend there. Let's go ahead and test it for some other data. All right, so there I'm gonna test it for here a crime, and thereafter I think we can remove. We don't need these things. It will automatically provide these axis label. So with this crime, we also see that it's a hugely skewed. At least these first room number and status population were linearly correlated in the middle of the data. But if we see in the crime, it's ultimately they're highly skewed at the center of low crime. It means to say that if no crime at all or less crime is happening at a particular place, then the price of a house is quite high for that place. And it's logical and obvious. And the place where no crime happens, that's mean those are the safest place. So of course the prices of house would be pretty much high. But there is no linear relationship between the crime and target output. So in that case, we have to do also some kind of the transformation so that we can establish here a linear relationship. All right. So this is how you can analyze these things, and we have now analyzed our assumption, and we found out that the sum of these, something like these and these variables are not following our linear assumption model. So we have to make here a transformation. All right. So we need to do here a log transformation. All right. So we are now going to do here a log transformation so that we can establish a linear correlation between the input features and the target feature. All right, now let's go ahead and see a log transformation of a variable. Previously, we had seen that room size, crime, and the L stat, these are not highly linearly correlated to the target output. So in that case, we have to do a transformation. And here we are going to do a log transformation. So we have here our Boston dataset, and in that we are going to use here a log crime for a crime dataset. So there np.log, and then we have there Boston, a crime column. All right, so in that way, a log of a crime, that's mean for this one will be stored there. Let's go ahead and run this. Thereafter, we are going to just plot this once again, but do remember we need to just change our this crime to log crime and see what happened there. Now once we do this, we see here, you see there, what's the difference there? We see a huge transformation. This seems a linear transformation, but this doesn't seem clearly a linear transformation. Though it is not, though this is not perfectly linearly correlated to the target output, but we can say that we have got an improvement over the original crime column. That's mean what we had originally, we have got here an improvement. And similarly, we can also do these things, log transformation, for other variables like this RM and LStat variables as well. All right. Perfect. So as of now, I don't need this log crime. So I'm just gonna I'm just gonna drop it. So I'm gonna just drop this log crime from axis is equal to 1, and I'm gonna enable here in place is true. That's mean it's gonna replace and it will remove this log crime from the Boston dataset. All right, perfect. So this is the how we can test our linear sheep test. All right, how we can do our check on linear assumption for a Boston dataset. In fact, you can do for any type of the dataset. And if you don't find a linear correlation between the input and the output variable, then in that case you can perform some type of the transformation to make it a linear correlation. All right. So we have done our testing on a first assumption, that is the linear correlation between the input and the output variable. Let's go ahead and calculate these linear assumptions based on the residuals. As of now, we are doing it based on the input and the output, the regression line fittings. But now I'm going to show you how you can do it by examining the residuals. All right, perfect. All right, now we are going to use our linear relationship by examining the residuals. That's the error. So these are the 4 steps which we can do. We need to make a linear regression model using the desired input variable, which is x, and then we will do a prediction, and then finally we will determine the error. Thereafter we will observe the distribution of the error. If the distribution of the error is a normal distribution, in that case we can say that there is linear combination between the input and the output. Otherwise, if it is not a linear combination, then in that case we have to also do some kind of the transformation to make it a linear model. So what's happening here is actually we are going to determine whether there is linear correlation between the variable input feature and target variable. All right. So these are the 4 steps which we are going to do there. So let's go ahead first of all do on our demo dataset which we have here, demo df. So on this demo df I'm going to use. All right. Perfect. So in the demo df we have input x and the output. So the first I'll show you error distribution for a reference, so that after that reference, if we plot the error distribution of a Boston dataset, we can make some reference to test whether it is linearly correlated or not. So the first of all, I'm going to create here a regression model. So in that case, I'm going to do here a linear regression, and thereafter I'm going to do here regression.fit. All right. So there I'm going to do here a regression.fit. I have here this input feature x, that's the demo df, and I'm going to pass this df. Now this is series data. If you notice there, this is series data, but we need their data frame data. So we need to put here a 2 square bracket. All right. So with this, it will be converted like this one. All right. Perfect. Thereafter, we are going to do here a demo def for our target output, which is y. Once we do a model fitting, thereafter we need to do here a prediction, and in the prediction we do res.predict, and thereafter in the prediction we need to pass our demo df. All right, that's the demo data frame. Thereafter we pass their input. All right. So since we are doing only on the training dataset fitting, so it's okay to find out whether we have linear correlation or not. Thereafter, I'm going to calculate the error. So how I can get the error? I can get this with the demo data frame. In the demo data frame, that's the true y value minus the predicted value. That's the pred value. All right. After that, I have got the error. Let's go ahead and do the scatter plot to identify how the residuals, that means the error, is distributed across the all value of a variable. So thereafter scatter plot x is equal to, I have there the predicted value, and in the y we have there in the y we have there a demo data frame, that's mean the true value. So with this we will get how it is linearly correlated or not. Thereafter the plt dot x label, in the x label, that's the predicted value, plt dot y label, and there we have this true value. All right. Thereafter I have there plt dot show. So what do you get there? You get here a clearly a linear relationship between the predicted and the true value. All right. So we can say that our test data set, that is the demo data set, it says that our input and the output are linearly correlated because the predicted value and the true value are linearly correlated. All right. So this is the one way to do this based on the predicted value and the true value. Now we can also do, if we do the scatter plot analysis on the error data. So for that I'm going to do here simply the plt dot scatter plot. Thereafter y is equal to, I'm gonna say there error, and x is demo df of the x variable. Do you see the difference here? We were doing on the target, true target value, but here we are doing the on the input value, because we want to analyze the error on all input values. That's mean how the error are varying based on the input values. All right. So thereafter we have a plt dot it's going to be the x label, and that's the residual, and this residual is actually errors. All right. plt the residual we are having on y-axis. On x label we have input feature. All right, input features. Thereafter we are going to do here the plt dot show. Let's go ahead and run this. It says that the key is missing. Let me see what's happening here. I think this the key, this for demo df, the key is missing there. All right, let's go ahead and run this. Once we run this, we see there it's a kind of the concentrated around the 0 in an input feature around the 0 and this residual. So the moreover we are much interested with this residual. We see there it's concentrated around the 0. That's mean this one is random error there, and it follows a normal distribution and the Gauss distribution as well. So the moreover, if residual predicted, if the residual, that's mean the error, that's the predicted values minus the true value, follow this kind of the pattern, that means there is a linear relationship between input variable and the target output variable. All right. So this is the one way to see this with the scatter plot. We can also see it with the histogram and distribution plot if we use their SNS. Otherwise, if you want to use only the PLT, so you can do the histogram there, and there I want to provide the input and the number of bins there I'm providing there 40. Thereafter I do there the plt.show, we get something like this. It says that yes, we have some kind of a normal distribution in this case, and we can also plot the KDE plot with the help of Seaborn. So there we have SNS dot distribution plot. There we have error, and then we have bins is equal to 30. Thereafter we have a plt dot x label, and in that case we have their errors, which is residual, then the plt dot show. So with this we get there a normal distribution, and which is almost like this one, and we can clearly see that our residual, that's the error, is following normal distribution. That's mean input vector or input feature space is linearly related to the target output. So this is the one way to do for our the demo data, but let's go ahead do it on our Boston dataset. All right. So I'm gonna say that do it on Boston dataset. So to do it on a Boston dataset, I'm gonna just copy it from here, and we are just gonna take here a single variable for the simplicity, and at the place of this demo data we have there a Boston, and of course there we will be having here a Boston. Thereafter this input feature X, I'm gonna use here lstat in our Boston dataset. If you remember, we have our feature, let's say we have these features, and in that features we have considered this lstat, rm, nitric acid, these things, and this crime we have considered. So I'm just gonna select this lstat, and the target output we have median value. All right, so mdev. Thereafter, sorry, it's actually median value. All right. Thereafter we have, for all these demo df, we need to replace this with Boston, and thereafter predicted is regression.predict Boston x instead of x. There it is going to be the lstat. All right. We can do one thing there. I think that would be much easy to do for me. That x is equal to, I'm gonna put this one so that I can utilize it for all other variables as well. And then perhaps I think, do we have any y? Yes, we have y, so we can't use. And do we have any x? Yes, I think we also have x. So I'm gonna say that their input x, all right, and then output y. So in the case of output y, otherwise I think this will be much better, Boston x and Boston y. All right, in the Boston y we are gonna use this one. So this is going to be now a simple part there. We have here a Boston x, thereafter we have here a Boston y. All right, and thereafter we perform the prediction once again on Boston x. Once it is trained, thereafter we are predicting, then we will calculate the error on the same data set. There is no train test split here. All right, perfect. Now Boston y, this Boston y is like this. All right, error is equal to the Boston y minus predicted values. Thereafter x is equal to the predicted values, y is equal to demo df, and then we have here a Boston y value. All right, plt.x label, there is the predicted values and the true values. So for the x label here, we are that's okay for this predicted value, but for this one we are going to set their Boston y. All right, so let's go ahead and run this. It says that there is error, and what's this error is there? Let me see. All right, it says that the error is coming in regression.fit. Alright, let me check that if it is performing well. So in that case, I'm gonna bring it out there. Thereafter, I also need to assess this one if it is working properly. Yes, this LStat is working properly. And I also need to test this one. And it seems that y, that's the target variable, is also working properly. There should not be any error there, though there is key error. So it seems somewhere, I think, there. Alright, so this demo df should not be there. So it's the Boston. Alright. Let's go ahead and run this. Now once we run this, what do we see there? We see there the predicted values, and there's the final target output price value, which is median value of house prices. These are linearly correlated at, you can say that till this 30, and there you can fit a line there, but thereafter there is error. That means some of the highly priced houses are not being predicted correctly. In that case, our predicted house price is somewhere around 30, but actual price of the house is somewhere around 40 and the 50. So at the end of our prediction, it is not doing a correct prediction. And in that sense, we can say that this LStat is not linearly correlated, or it is not linearly correlated with the target output. And we can also verify that with our previous assumption check, where we had checked that this LStat. Let me show you where we did that. Yeah, we did there. So there, do you see there, it was not highly correlated. There were some correlation, linear correlation, but at the start of their house prices, where house prices were pretty much high, at that place it was not able to predict the, it was not linear. And the same thing is happening here. When it is not a linear, then in that case it is not able to predict it correctly at the last of, at the for the high house prices. All right, perfect. So this is how you can test that whether your input and the output are linearly correlated to each other or not. So this is about the linear correlation between the predicted value and true value. Now let's go ahead and do the analysis of the residuals as we did earlier. Like here, if you remember, we had done the analysis of the residual. So the same thing we are going to do there. Now if you remember, we already have here error. So the error is not going to change, but there we need to change this to a Boston dataset, and this input has to be the Boston X. All right. Thereafter, everything seems same. There is no issue. And if we plot this residual error, and we see there is some concentration around the 0. Do remember, we only need to look around this column. We don't need to look this one. So on this axis, there is 0. If we see there, so mostly it is somewhere you can say that, okay, there is something around the 0, and but still there are some error on the input feature which are less or large there. So those are deviating. All right. So those are deviating from this 0. So it seems that it is not actually a normal distribution of the error. And if you want to check the normal distribution of the error, we can use this sns.dist plot. So in the dist plot, there is error, and bins is equal to 30 we are using there, and it says that it's not exactly a normal distribution because it is highly concentrated somewhere around 5. If you see there, it is concentrated somewhere around 5, and there is some peak which is happening around you see there the 20. That's when there is 20. And if we see there, so these are creating a little peak there around the 20. And thereafter 30 and 35. So it's ignoring some values out of the 35. Otherwise, you can also get some peak there as well. So the moreover, we can say that this is not the normal distribution. Now this lesson has been almost 40-50 minutes long. You might be feeling bored, but one thing is clear here is that you have learned a lot of the things there. How you can calculate your input, how you can make sure that your input data is highly correlated with the target output. Unless and until you have a linear relationship between your input variable to the output variable, it's not going to work in a linear regression. All right. So we have to do some kind of the transformation for this as well, so that we can do a proper analysis there. All right. Perfect. All right. Now let's go ahead and try some kind of the transformation so that this distribution can be seen as a normal distribution. So the same thing we are going to do from here. We are going to just copy the whole thing there. And I'm going to give a new heading that log transformer for LStat. Alright, so for LStat, I need to do a log transformation. One thing I'm missing there, I should keep that in that column as well, so that if I need to change my input and the my input variable, I should be able to change it. So this one, if you remember, this LStat is do not have a linear relationship between input and the output. So we need to make sure that it should have a linear relationship. If you remember previously, we had checked for the crime data. So for crime column, we did log transformation. So the same type of the log transformation I can do there. np.log transformation of this whole data set. Only this thing I need to do. Thereafter, in the prediction, I also need to do the same thing. All right, so that's the prediction is happening there, and I'm doing there the same thing for the predicted value, and other things should be okay without any issue. Let's go ahead and run this. All right, thereafter plt.title with log of LStat. Let's go ahead and run this. It says that there is value error. I think perhaps inside this. All right, it says that still there is error. Let me check that. Where is that error? Let me check that. I'll get back to you. Seems like I'm getting the error here. So it should be like this one, I think. It's okay. There should not be any error. All right, now do you see there? Earlier I think it was wrong there. But now if you notice there, this predicted value and this the mean house, the median value of a house is somehow linearly correlated. Earlier it was not able to predict after the 30, but now it is able to predict after the 30, and it's kind of a much better than what we had seen earlier. Now we also need to do the kind of this plot to see that whether it is happening actually or not. All right. So with that, if we do like this, we see there a huge difference between this and that. So this was somewhere skewed toward a 5, and there was a peak around the 20. But now if we notice, it is somewhere around only 1 or the 2, and the peak around the 20 has been gone there. So moreover, with the transformation of log transformation of L stat the column, we have gained a linear relationship between the input and the output variable. So if we use a log transformation for L stat, and previously we had also seen for crime, if we use log transformation, we can definitely improve the accuracy because it is establishing there a linear relationship between the input and the target output. All right, perfect. So we have seen our linear relationship between the input and output with the various ways by establishing a regression line and by the analyzing residuals or the errors. So we are done with our linear relationship establishment and the check of linear assumption. Now we are going to check the assumption of non-multi-collinearity. That means there should not be a collinearity between the input feature space. That means the more than one feature space, two or more than the two feature or input feature should not be correlated to each other. Do remember what we are talking about. We are talking about input and the output should be a linear correlation, but input with the another variables of the input, there should not be the correlation. All right, there should be correlation between input and the output, but should not be any correlation between the input data. So that's the problem of multi-collinearity. So we'll cover now multi-collinearity. To calculate the collinearity, we need to evaluate the correlation between all input data. For example, we have our Boston dataset here, and if we see the columns of Boston dataset, these are the input features, all right, till this one, and then the final one is the target output. So there should not be any multi-collinearity between all these input features other than this output feature, all right, which is target variable, or you can say the median house price value or median value, which is house price. All right. So earlier we had talked about the linear relationship between any of these input features with the output feature, which is target output, but there should not be any correlation between any of these input with other inputs. All right. So I mean to say that in between these features which we have here. And if you want to calculate if multi-collinearity is present, we need to calculate correlation matrix between these features, and thereafter we will plot it by using a heat map. All right. So let's go ahead and calculate there a core mat, that's the correlation matrix. In the correlation matrix, we have here a Boston data set along with all these features. All right. Thereafter, we have these features, and then we are going to calculate the correlation, and then finally I'm going to round to 2 decimal places of these correlation. All right. Thereafter, if you see this core matrix, you will get something like this. So this is another data frame. In the data frame, we are having the values with the correlation. So the crime with the crime is correlated with exactly 1. That means it is highly correlated. So all of these diagonal element value will be 1 because we are getting the correlation with the same value. But other than the other than this main diagonal, other values should not be highly correlated. But there are few values like 0.5. So we can say that till 0.5 it's okay, no problem. But if values are more than 0.7, like here we have 0.71, 77, 75, so these are highly correlated, and these values should not be this much of correlated. That means to say that this age and the distance, these are highly correlated. Do you see this? The age and the distance is quite correlated to each other. And there are many other values which we can see with the histogram. So let's go ahead and plot here histogram. So for the histogram, I'm going to do simply here plt dot figure. All right, so this is the plt dot figure. Otherwise you can do like this one, subplots, plt dot subplots. In that I'm going to set there a fig size. All right, that's the figure size. Inside that I'm going to set 10 cross 10 figure size. Thereafter I'm going to say here the sns dot heat map. All right, so in that heat map I'm going to pass there data is equal to this correlation matrix. Let's go ahead and run this. Once we run this, we get something like this correlation matrix. And with this, we see there, those are light color. So these are the bright color. That's mean the highly correlated. And the darker colors are also correlated. These dark colors are also correlated, but these are negative correlation. All right. And these kind of the red color, these are the so-so. That's mean around the zero correlation. So we are also going to put the annotation so that we can see inside this how much correlation is there. All right. So for that purpose, I'm going to put this annote is equal to true. And thereafter, I'm going to say just plt.show. And now if you see this, you will get there the exactly all these numbers. All right. So do you see there these numbers are there? All right. But one thing, do you notice here, the thing is that these plots are not getting correctly plot. There is a problem. So there is it is getting clipped after half of this data. So that's the problem. And you see there, it is also getting cropping. So it is getting cropped there. So we need to actually fix this problem first. All right. So if you are also getting something like this or a similar problem, so there is a solution. So it's actually a bug if you see on a Stack Overflow. So there is a problem something like this. It is happening because of Matplotlib 3.1.1. Currently I have installed this version of Matplotlib. That is why it is creating a problem. But later on it might get fixed. But by the way, if it is not fixed for you, you can try this solution. So this solution says that if you do this one, so we can simply just copy it from here and thereafter we can do it here. All right. So if you do this something like this and there is axis, so we need to also make sure that we are getting that axis correctly and that we should get it from the heat map. All right, from here like this. Now there should not be any problem. All right, so do you see this? Now it has correctly fixed this problem. There is no issue here. All right, perfect. So here what we get, these darker color and the brightest color are showing a most correlation between these variables. And apart from these one, do you see there 0.91? That's the between radius and the tax pair. So between radius and the tax, it's quite high correlation. So we should not take these two variables together in the regression problem. We should at least drop one of these variables, either a tax or a radius. Other than that, there are some other variables which are greater than 0.7. These are variables like this nitric acid and there is another one, this distance is high, age and distance is high. Then of course we have this age and distance, that's okay, no issues. And there is this one. So these few variables are highly correlated to each other and that should not be there. Otherwise it might create some problem later on. All right. So that is how we check the multi-collinearity problem between the input vectors. All right. One more thing, if you notice there, the L-stat and the crime. Do you see there? There is L-stat. There is L-stat and the crime, which is around 0.5. That's okay. no issues. So we can take the LStat and the crime together for the output prediction. Other than that, we had also seen that RM, so the RM and LStat is around 0.61. 0.61 could be a problem. Otherwise, we can take, but we should make sure that we should not take any of the variable which have more than 0.7. All right, so we can take this one, but it could be some problem. Other than that, if you notice between these RM, we can also take the distance as well, this radius, taxpayer, and this one. So along with this LStat, if we want to take, all right. So, and the correlation of this RM with other variables. All right, do you see there the RM with other variables? It's almost okay without any issue. There is only one variable which is LStat. So this RM is getting high correlation with only one variable. Otherwise, it is mostly uncorrelated with other variable. So this RM is quite good choice to take as the input, feature input for your machine learning model prediction. And other variables like this one, do you see their distance? It is having highly correlation between at least 3 variable. Do you see their indus, and there is nitric acid and the age. So we should avoid these type of the variable. All right. And apart from that, if you notice their radius, we can take the radius, but we should avoid taking the tax along with the radius. If we take the radius, we should not take the tax. All right. So these are some intelligent solution to remove the multi-collinearity between the inputs. Now let's go ahead and plot the correlation which we had just seen there between the radius and the tax. All right. So do you see this radius and the tax, which is highly correlated, and see how it is correlated on a regression line. So regression line we can get with the LM plot, and there we have x is equal to radius, and there y is equal to, we have here a tax. Thereafter data is equal to Boston data set. There now we have order is equal to 1. So thereafter, once you run this, you will see it is highly correlated. So the correlation is quite high between the radius and the tax. So we should avoid this problem. And apart from that, if we take the correlation between the distance and the nitric acid, there do you see this nitric oxide? Actually, this is nitric oxide, and along with the radius, there is 0.61, and there is a distance. So this distance is quite high. That's the 0.77. So if we see that SNS dot LM plot x is equal to nitric oxide, and thereafter y is equal to, there is distance, and then data is equal to Boston. All right, there you get order is equal to 1. All right, so with this, what happened here, what do you get? This distance, and there is nitric acid. All right, so these are also highly correlated, these two variables. So we should take only one out of these two variable, only one variable out of these two variable. All right, so we should avoid all these multi-collinearity while selecting the features. Perfect. So we have covered successfully multi-collinearity in the feature space. Now let's go ahead and discuss about the normality. So we'll discuss about the normal distribution of the feature vectors and Gaussian distribution of the feature vectors. We will be also testing these Gauss and the normal distribution with the help of QQ plot. All right. So now we will evaluate normality using histogram and the QQ plot. So let's begin first with the histogram. Thereafter, we'll see if variable is normally distributed. We should observe there a typical Gauss-Weil shaped plot, something like this. Otherwise, it will be skewed either right at the left hand side or right side. All right. So we'll evaluate this. So the first of all, I'm gonna set here a reference with the help of our demo data, which we already have. So the SNS.distribution plot, there we have the demo data. Inside that we have there X and the number of bins here. I'm gonna have here 30. Now if we plot this, so we see something like this, and at this plot what we see there, we see it is distributed along the 0, and it is quite okay with the normal distribution. There is a little mismatch, but as we increase the number of data points, it should follow that a perfect normal distribution. But moreover, we can assume that this is a normal distribution on our reference data, which we had already created for our demo. Now let's go ahead and calculate the reference for our selected features which we have been evaluating. The features which we have been evaluating: number of rooms, LStat, and the crime. So these few features we had explored. All right. Now let's go ahead and check this one. So the first of all, I'm going to do here this SNS.dist plot. All right. So SNS.dist plot, there I have here a Boston. In that I have room number, room size, you can say the average number of rooms per houses, thereafter number of bins is equal to the 30. All right. Now let's go ahead and run this, and once you run this, you will see something like this. So the moreover, we can say that this room is normal, following a normal distribution. Although it is not perfectly a Gauss distribution, but after doing a standardization, it will follow. But yes, this is a normal distribution, so I don't think that there is any problem with the average number of rooms in case of variable normality. All right. Now let's go ahead and check the histogram of our other variable which we had considered earlier. That's the LStat. So in that case, I'm gonna just simply copy it and paste it here, and then I'm gonna provide here this LStat. So in this LStat, we see that it is not normally distributed. Although it seems that it is normally distributed, but it is a skewed distribution. So it's skewed at left hand side, and this is not gonna produce a good result when we predict the target variable, which is the median house price value. This is not gonna predict it correctly. So in the test of normality, this LStat has failed. So we need to do some kind of the transformation. As I had earlier shown you that I had done a log transformation to convert it into a linear relationship between the output variable with this LStat variable. So the same thing I'm going to do here, np.log, and after doing this log, it should be able to follow a little better a normal distribution. Now at least what we see here, it is highly skewed to the left hand side, but at this side now we see that it is skewed at the right, but not at high as it is skewed in this graph. So we can say that there is some improvement over the previous data which we had earlier. So the previously with other assumptions, I had also proved that the variable transformation has helped us to establish a linear relationship between the target and the input. And with this log transformation, we can also say that the somehow at least in a more better position than what we had earlier. So it's better than the previous what we had. All right, perfect. So this is how we can check the normality based on the distribution plot. Now I'm gonna distribution plot, or you can say the histogram. Now I'm gonna show you how you can check it with the QQ plot. All right. Perfect. So this is the QQ plot. Earlier we had tested it with the histograms, and this QQ plot should be like this. All right, perfect. So in the QQ plot, we need to first understand the few things. In QQ plot, the quantiles of a variable are plotted on the vertical axis y, and the quantiles of a specified probability distribution are indicated on the horizontal axis x. So we can plot this QQ plot by using stats library. So we have stats dot probability plot, which is prob plot, and the first I'm gonna do it with our demo variable, which we will be using for our reference, and distribution is equal to, here I'm gonna use a normal distribution, and thereafter the plot is equal to the PLT. That's mean the matplotlib plot, it is gonna plot there. All right, let's go ahead and run this. So we get something like this. So what is the mean of this? What does this mean? This says that we have a theoretical quantiles, and there we have our ordered quantile. And if the variable distribution are normal, then we will get there a line, a fitted line. You can say it is regression line otherwise, at a 45-degree exactly. So if it is at a 45-degree exactly, that mean to say that it is a normally distributed. And if this plot, do you see there, this line is 45-degree, and there is the data distribution along with this line, that's mean it's a 45-degree distribution. And if it is not along with this line, that mean the data is not normally distributed. Let's go ahead and check it for our distribution on the Boston data set. So there we have here the Boston. So in the Boston, I'm gonna simply use here the RM, that's the average room number, and let's go ahead and see this. So what do we get there? We get there, it is normally distributed in middle, but here at the start and at the last, it is not normally distributed. So there is a problem in this case. And we had also seen many times previously that this RM is not normally distributed at the end and at the start. But we had assumed that it is normally distributed, but still if you notice there is a little skewness. But moreover, we can assume that. So the same thing we can do that. Apart from that, the few data points at the start and at the end, otherwise it is normally distributed. And similarly, if we check it for other variables, like let's say LStat, we see that it is highly deviated from this 45-degree line. All right, from this line. So it's not normally distributed. It says that clearly there is a huge deviation. In this case, it was okay. Otherwise here, there is a huge deviation for a lot of the data points here and there. And the same thing we can notice for LStat. It's not a normal distribution. There is a skewness there toward the left side. The same thing we can visualize it here. And apart from this LStat, we have been also seeing for crime as well. We can also see it for crime. So if you see in the crime, it's not distributed. There is no point actually. It first starts coming like this, thereafter like this. So there is no follow-up. At least in this, it has followed for some point here. All right, in LStat, but here in the crime, it is not following any of these rows. So the moreover, in this case, it is not normally distributed, which we had seen previously that the crime variable, the data column crime, was highly skewed toward the left side. All right, now let's go ahead and see if we can solve this skewness by using a log probability, by taking a log of this. We had already seen that we can solve this by taking the log for LStat. At least we can get a better plot, but not the perfectly, but at least it would be a better plot than what we had earlier. So the np.log, if you see there the lstat, so we are getting lstat something like this. There is highly non-linearity here and there. So, but if we take the log, we see that it follows the somehow there is just a little data which is deviating from the normal distribution. So the moreover, it established that if we take the log of lstat, then in that case, we might be able to get the better result than by using exactly the same data set which we had earlier. All right. So the same thing we can do for our crime. I'm gonna put that here, and there we have np.log, and if we plot it, now at least here it was not following this one, but at least here if you notice, the somehow at the some level, not exactly for all the level, but at some level it has tried to follow this normal distribution. Otherwise it's definitely not following the distribution, but the somehow it is better than in the some cases it is better than that. So it's always better to take the log of this crime, room average room, and the lstat. All right. So you can also investigate other variables for these normal distributions and the linear relationship between the inputs and the output. And similarly, you can do the transformation to establish the good relation between the input and the output. All right, perfect. So we have seen our homogeneity. We have seen our normal distribution. We have seen normal distribution. We have seen linear regression, and we have seen the previously with how we can establish the linear relation and how we can find out whether it is following the linear relation between the input output. So all these things we have seen here. All right, perfect. Now we are gonna see how we can test for homogeneity. Do you remember I told you that at the start of this lesson that we will be testing on a 4 scale. The first we will be testing, is there any linear relationship between input and output? That's the linear model assumption or a linear data transformation assumptions, which we in general make that there is a normal distribution and there is a multi-collinearity, which we had seen, and the last one is the homogeneity, which is also homoscedasticity. All right, so let's go ahead and see the homogeneity. All right, so to identify if a particular variable is homoscedastic or it is homogeneous, we have to make a linear model, a linear regression model. Thereafter, we need to predict the final output. Then we have to calculate the error. Thereafter, we will plot it versus each of the independent variable. And if a variable is homogeneous, then we will find that the error is homogeneous. That means to say that, let's say if we predict the final target output, which is the median value of a home price, and the error on the predicted values, if we plot versus each of these columns like lstat, the crime, and others, and if error are homogeneous, then in that case we will find that okay, the variable is homoscedastic. All right, that's mean the variable is homogeneous. So let's go ahead and first we need to do our linear model fitting. Thereafter we will do the residual calculation. All right, so the first of all we have to make sure that we divide our data set into the train set and the test set. Thereafter we will fit our model. All right, so we have here x train, there we have x test, y train, y test is equal to train test is split, and in that we are gonna pass here the Boston, and inside the Boston data set we are going to take here the 3 variable which we have been taking for our analysis: RM, lstat, and thereafter I'm going to take here the crime. All right, thereafter this is for the input. Let's go ahead and take it there. That is for input, and then for the output I'm gonna get it for Boston, and there is median values. All right, that's the target output. Then the test size, I'm gonna having here the test size is equal to 0.3. All right, and then here we have the random state, all right, is equal to the 0, so that we can reproduce the same result. Let's go ahead and run this. Thereafter we are gonna get the shape for X train and the shape of X test. All right, there we have 354 rows which is in X train and 152 rows in the X test. All right, so now we are going to do the standard scalar. That's mean we are going to do standardization. So by doing the standardization, we will try to make sure that all the variables, these input variables, are in a same scale. Otherwise, if they are in a different scale, they are going to affect these output in a different scale. But the weightage of all these variables should be the same. So in that way, we have to make sure that we do the standard scalar. All right. So there scalar is equal to the standard scalar, and thereafter I'm going to do here this scalar dot fit, and this I'm going to do on the training data set. Thereafter we get here a scalar. All right, then we can do the transformation for the train data set and the test data set, which we will do later. All right, so let's go ahead, and as I told you that to test this homogeneous or homoscedasticity, we have to first build our linear regression model. Thereafter we need to do our prediction, and then finally we have to calculate the error. All right, so there I'm gonna build my linear model. So the regression is equal to the linear regression. Thereafter I do the regression dot fit, and in this fit I'm gonna do here the scalar dot, we have already done the fit, so I'm gonna do here the transform. All right, so the transform, and then finally I'm gonna do here this transform of X train, and then Y train is going to be the same without any issue. All right, let's go ahead and do the test for the train set data. All right, thereafter I'm going to do their pred is equal to the regression. All right, dot predict, and sorry, this should be the predict, and in that I'm going to do the prediction for the first X train data. Thereafter I'll do the prediction for the X test data. All right, so this prediction is for the training data set, do remember, and for this training data set I'm gonna get the error, so the mean square error. All right, perfect. Thereafter I'm gonna here do a print, and then I say there a linear regression MSE. All right, so there I get something like this, linear regression MSE. Otherwise I can do something like this without any issue. So there we have a mean square error. In that I need to pass the Y train, and then finally pred. All right, so if I run this one, it says that there is error. Let me see what's the problem is there. All right, so if we are getting this kind of error there, SVD did not converge, so it means that I might have there's some infinite value or null value. So I need to also first test that one, and if I run this one, I do see that there is no issue. Otherwise, if it is not producing any issue, that's good. If I check this xtrain is null and sum, it still says that I do not have any issue there. All right, so it's okay. There should not be any issue. Let me run this again and see. Well, so at the second time when I run it, there is no problem. I don't know what was the problem the first time. All right, so the moreover, I did not change anything, but still it has worked. That's magic. All right. Now let's go ahead and this is for a training data set. And for the train data set, the MSE we are getting there, that's the 28.60. Let's go ahead and perform this for the test data set. All right. So there I have test set data, or you can say the test data set. In fact, that should be all right. Train data set. All right. So there I have this should be x minus x test data. Thereafter, we should calculate it between the y test. All right. Let's go ahead and run this. So what do we see there? We see that there is 28 in a training set and the 33 in the test set. All right. Let's go ahead and calculate the error. So their error, we are getting y underscore test minus the predicted value. That's the error. But the one thing, do remember, you need to note this. And one more thing you need to pay attention on that. While calculating this homoscedasticity, we have not taken any kind of the log, and we have not done any kind of the normalization on the data. There is only standardization. All right, so there is no data transformation. So this is being done on the original data, and since on the original data we are getting this much of the MSE, that's the mean squared error, and if we do the transformation on the data, we should get a less error. That's mean a low value of MSE. All right. Perfect. So we have their error. Thereafter, I do there the PLT dot scatter, and thereafter x is equal to x underscore test, and then I have their L stat. So I'm gonna do it for the L stat, and then y is equal to error. All right. So I'm gonna do it for only one variable, L stat. Thereafter the PLT dot x label, and in the x label I have there the L stat, and then the PLT dot y label, and in the y label I have there the residuals, which is also error. All right, let's go ahead and plot this. So when I do plot this one, what do I get there? So we see this is 0 line, and mostly we see that the distribution is somehow somewhere around the 0. All right. So we say that, okay, the variable L stat is kind of homogeneous, but we can't say that it is exactly the homogeneous. But yes, there is high probability that the variable is homogeneous, and there is a homogeneous distribution across the variables, although there is less concentration here and there are few the outliers, but otherwise it seems okay. So the moreover we can say that yeah, it's okay for this one. But if we test it for a crime, do you remember the crime was highly the skewed data? All right. So if we test it for crime, we get something like this, and in the crime we say that, oh, this is not a homogeneous. That's mean there has to be some kind of the transformation on the crime if we want to make sure that our model follows the rule of linear model assumptions. All right. So this is not working in the case of crime, and similarly you can check for other variables. And if we do the distribution of the error, And if we do the distribution of the error, so what we get there, let me see there, the SNS dot dist plot, and their bins are 30. Do you remember previously we had also done the same thing? And it seems like, okay, it is skewed in the left hand side, all right, and it is not highly skewed because we have there the L stat as well, which is producing good result. And apart from that L stat, we have crime and the RM. So this crime is creating a little problem. So because of crime there is a problem. Even if we remove the crime, this should this will be more like a normal distribution. And other than that, if you want to make sure that this follows a normal distribution by even including this crime, we need to make sure that we do some kind of the transformation here. All right, now finally we are going to do a transformation on log transformation on all of these three variable. Do you see there all of these three variable, so that we can correctly we can get a better accuracy. So the better accuracy means in a regression we don't have any term like accuracy, but we have this mean squared error. So lower mean squared error means less error. Less error means a better model. So we are going to follow a transformation, and I'll show you that how you can reduce the error. All right. So there I have this one X train, and the same thing I'm gonna just copy everything from here. Once we get that, thereafter we need to do this scalar fitting as well. So I'm just gonna copy and paste it there. Once we do this scalar, and thereafter we are going to copy this one. All right, and we get something like this. So the thing which we are going to do, we are going to perform a log transformation on these variable L stat, RM, and the crime. Do remember, you might not need to perform the log transformation for all the variable, so choose it carefully. Let's say I have these and I need to do here np dot log, something like this. And if you do that, it takes the log for all these three columns separately. So the same thing, I'm gonna do this. So I'm just gonna copy it simply from there, and then finally I'm gonna paste it here. All right. So once you do this, thereafter I'm gonna finally run this one. All right. So once I run this, it once again says that perhaps the same error. I might need to run it again. All right. So do you see this? What is the advantage we have gained here? We got on the train set a 24 only MSE. Earlier on the train set, this MSE was around the 28 or 29. And on the test set, it is the 33. Now this MSE has been reduced to a 29. That's mean there are gain of MSE 4. And do sorry, and do remember, a low MSE means a better accuracy. All right. Perfect. So this is the way how you can analyze your data, whether it is following linear assumption in the case of linear regression and other linear machine learning model. Whatever linear machine learning model you are using, your data should follow a linear assumptions. So there were 4 linear assumptions which we had analyzed in this video. The first one, there should be a linear relation between input and the output. There should be a normal distribution. There should not be any co-linearity, and the variables should be homogeneous. All right. And now to test for the homogeneous, as we see there, there were not a homogeneity there. So what I'm going to do here, I'm going to just get this error from there, and there I got this error. And now this error also follow, it's much more accurate than the previous one what we had. Thereafter I'm gonna show you this one. All right, on the crime. So on the crime, earlier we had a very much skewed graph for residual plot, But now I'm gonna show you if we take the log, since we have already taken the log for the training of the dataset. So we also need to make sure that we take the log here as well. So there we take the log so that we can plot the correct data. Now if you take the log there, you get something like this. All right. So we get here not bad as we had seen previously, like this one, but yes, we do get something like better than that. All right, do you see there? So it's much better than the previous one, but it is not exactly following a homogeneous rule, but it's much better than that. And this has reflected in reducing the mean error there. You see there, the mean error has been reduced previously without any kind of the transformation. But still there are some outliers, and we need to handle these outliers correctly. So in the coming lessons in this video series, a feature engineering video series, I'll be showing you how you can handle outliers, such type of the outliers. Alright, so thanks a lot for watching this video. It has been almost a 2-hour long video. Thanks a lot for watching this, and please do like this video and subscribe this channel so that you can get a notification directly into your inbox whenever I publish new videos. Bye bye, take care.